Hello and good evening. So in this video, we're going to be talking about the math behind acids and bases in chemistry. So I guess the first question here would be, what are acids and bases? So this guy named Arrhenius, many hundreds of years ago, came up with, there are a few things that make them different. Acids are substances that have a pH less than 7 and a pOH greater than 7, whereas bases are the opposite. So their pHs are greater than 7 and their pOHs are less than 7. Now, what this means, we'll get to in a bit, but just remember that for now. Similarly, they taste opposites. Acids taste sour, for example, lemon juice, tomatoes, these are acids, and bases would taste bitter, so soap or sodium bicarbonate. And the definition that Arrhenius gave is that acids release H plus ions, so hydrogen ions, into the water, whereas bases release OH minus ions into the water. So OH minus would be referred to as a hydroxyl. Now, this is Arrhenius's way of explaining it. Using other different definitions of acids and bases, we can say they don't necessarily have to release these things all the time, but it's a good way to look at it to start. So if you notice here, actually, the H plus ions that we're talking about for acids and the OH minus ions from the bases, so the hydroxyl, when you add these two together, you end up with water. And this isn't a coincidence because these halves are basically just when water splits. Because in fact, water does split. Like if I just have a bottle of water, the water is constantly splitting and coming back together. So it's splitting into these H plus ions and these hydroxyls. So what this means here, well, first off, we have a pH and a pOH scale for reference. And keep in mind that you can't realistically have pH and pOH values less than 0 or greater than 14. Those are just written there for reference. Now, with these values, you can see that water, as we mentioned earlier, is both an acid and a base. It's exactly in the middle of both of them. And this is basically because, as we said, it breaks apart into both the H plus, which is an acid, and the OH minus, which is basic. And they sort of cancel each other out. It's both at the same time, right? It's both an acid and a base. So we call water amphoteric to explain this. Now, to calculate these values, our first thing is, well, equations. So pH can be set to be equal to negative log base 10 of the concentration of H plus, and pOH is the same, but of the concentration of the hydroxyls. So these concentrations are written in molarity. So to find molarity, you take the moles of the solvent, for example, the moles of H plus or the moles of hydroxyl, and you divide it by the liters in the solution. So if I have a 0.5 molar solution, that means that there's 0.5 moles of whatever inside of it per liter. And now these pH and pOH scales are always in between 0 and 14, as we already mentioned, and adding them together also always equals to 14. And the reasoning behind this is that whenever you multiply the concentrations of the H plus and the OH minus together, you will always get 10 to the negative 14 for these solutions. So as an example here, we have a solution of concentrated H plus, and it is at 10 to the negative 4 molar concentration. So to find the pH, we take the negative log base 10 of that and find 4. So the pH is 4. And since we know 14 minus the pH is going to get us the pOH, we can find that the pOH in this situation would be 10. So now a few examples. And go ahead and pause the video to try and solve this. Okay. So what we're doing here is we're applying the concept we just went over, but we're doing it backwards. Now we know that the pOH is 5. First off, we're going to convert that into pH. So 14 minus the pOH is the pH, in this case, 9. Now that we've found the pH, we're going to set that equal to its equation, negative log base 10 of the concentration of H plus. As we can continue to solve this, and ultimately we'll get that the concentration of H plus is 10 to the negative 9 moles per liter. And now it's another practice problem, But this time, I don't want you to convert directly between pH and pOH, and I want you to maybe go back to those slides and see if you can solve this a different way. All right. So to solve this problem in sort of a different way from before, the previous method still works, but this time we're going to go from pH directly to the concentration of H plus. So once again, we're going to set them equal, and we're going to find that the concentration of H plus is equal to 10 to the negative 2 molar. Now, using this number, we're actually going to use the equation we mentioned earlier, which states that 10 to the negative 14 molar is always equal to the two concentrations multiplied by each other. So by plugging the H plus concentration in, we can then find the OH minus concentration, which is 10 to the negative 12. And so we found the OH minus concentration. So for example, from here, maybe if I wanted to find the POH, I could just take the negative log base 10 of this, and I'd find a POH of 12. So now that we've gone through all this math, it's very important to know why this is relevant. First off, if we collect any one of these values for a solution, we can know a lot about it, right? We can know how much of all these different things there are, how strong of an acid and base it is, and well, whether it's an acid or a base at all. And later on, if we collect experimental data on concentrations, we can use this to help quantify the acidity of the solutions. So once again, as I said, let's say we were given a solution. By using a test strip, we can find what the pH of it is. And from there, we can find what the pOH. We know how strong it is. We have all these other values that we can derive. And off of this, later on, you're going to learn about this thing called acid-base equilibria. And what this does is that you can often guess what the actual acid or base in the water is that is causing this change. And speaking of which, if you're curious about this topic, I recommend that you search up acid-base equilibria. It's a bit of a difficult topic, but using it, you're able to estimate, well, not even estimate, you're able to predict how acidic or basic a solution will be if we add a specific substance to it, given the right numbers. And thank you for watching.